Hey everyone, it's Dr. Walker. This is an example from video 53C on the center of mass. In this example, we want to find the center of mass of an extended object. We have a uniform rod and we want to find the center of mass for the first part. Uniform means that the mass is evenly distributed. The second part is going to be a non-uniform rod, so the mass is not evenly distributed throughout the rod. Let's look at the first part. So to find the center of mass, first of all, the rod is only along the x-axis, so we don't have to worry about any y or z directions. We can find the x position of the center of mass. The y and z position are 0. So with that said, we can write down the equation for the x coordinate of the center of mass, which is 1 over the total mass times the integral x dm. So how in the world do we integrate this? Typically, when we're doing one of these integrals, we want to change the dm so that it's in terms of length rather than mass. If dm is in terms of dx, then we can integrate along the length of the rod. So the trick for doing that is to realize that there's this variable called the linear mass density. That's defined as the mass per length. So this is very similar to the density that you may be familiar with, mass per volume, right, which uses the letter rho. So this is just a mass per length instead of mass per volume, because the mass is distributed over a length instead of a volume. Okay, so now what we do is we solve for m, we get lambda L. And now we can write an expression for dm. If we have a small element of mass that we call dm, then it's going to equal to lambda times a small element of length, which we could call dl. But in this case, the small elements here are going to have a length equal to dl, which is dx. So we can just call it dx. And that's how we're going to get rid of the dm and bring in the dx so that we'll be able to integrate. Remember the idea behind this integral when we came up with this expression? We said when we have our extended object, we're going to break it up into a bunch of little mass elements. We said that those mass elements had a mass delta m, but now we're just changing that to dm because we have the integral. So we said that we're going to break up our object into a bunch of little mass elements, and then we're going to integrate to find that position of the center of mass. So that is the main thing to realize, is that we want to change this integral so that it's in terms of dx. So now it becomes x lambda dx. So we are taking the integral with respect to x. Lambda does not depend on x because we have a uniform mass density. So that means that we can take lambda out of the integral. So we have lambda over m, the integral of x dx. So now we can go ahead and integrate. Now we do need to put our limits of integration. What are we integrating from and to, right? So the way you think about it, just think about your small little mass element, and usually you just draw one. So the one has already been drawn for us. And you think about, well, where does it start? It starts right here where x is equal to 0. And where does it end? It ends at x is equal to L, the length of the rod. So we know that we're going to integrate from 0 to L. When we integrate x dx, we're going to get x squared over 2. So we're going to have lambda over m, x squared over 2, and take our limits of integration from 0 to L. And that's going to give us lambda L squared over 2m. The 0, 1 cancels out to 0. So we would think we're done. However, we can make a little simplification since we know that the problem didn't give us lambda, and typically when you write down your answer, you only want it to be in terms of the variables that are given in the problem. The problem gave us mass and length. So, since we know that lambda is mass per length, we can go ahead and make that substitution. So we're going to have mass per length, and then we're going to have lambda squared over 2m. And now we can go ahead and simplify. The m's are going to cancel out, and one of the l's is going to cancel out, and we're going to get L over 2. This is exactly what we expected. The center of mass of a rod, where the mass is uniformly distributed, is going to be right at its center.